Hi, everyone. Today, we would like to introduce a high-performance system for large model training developed by HPC-AI technology. The system is called Colossal-AI, which is designed to be a unified distributed AI system for the big model era. So, HPC-AI Tech is a global company focused on increasing AI productivity and building a world-class distributed AI development and deployment platform that enables cloud platforms, supercomputers, and even your own GPU to serve AI at a much lower cost. The company was founded by Dr. Yang Yu, who received his PhD in computer science from UC Berkeley and is currently the Presidential Young Professor at the National University of Singapore. I am Professor James Demmel and Chief Strategy Officer. I am also the Richard Carl Demmel Distinguished Professor of Computer Science and Mathematics at UC Berkeley and former chair of the ECS department. Our shared goal is to make large-scale machine learning much more efficient and accessible to users. We have set up 2 offices in Beijing and Singapore and built a team with 30 employees with computer systems and machine learning backgrounds. So, we will follow this agenda for our presentation today. We're going to give you some background on what are the challenges that our system is trying to solve, what are the existing solutions, and why they aren't sufficient, what are the new efficiency techniques that are in Colossal AI, how we make sure that they're all easy to use, and then give some examples of the outstanding performance that we achieve. So here are some of the backgrounds and challenges in the deep learning community and the resulting challenges faced by today's AI engineers and researchers. So, as all of you know, deep learning has now become an important technology in industries such as e-commerce, autonomous driving, pharmacy, and many more. This graph from a study by OpenAI plots the amount of compute needed to train a model on a log scale versus when the model was introduced on the x-axis. As you can see, the amount of compute used in the largest AI training runs has been increasing exponentially at a rate of 35 times more every 18 months. This growth far exceeds the Moore's law growth, which is 2x every 18 months. This means that specialized hardware, like single CPUs and GPUs, can no longer keep up with this growth. If we focus on the past few years, deep learning models have continually ballooned in size. This graph plots on the vertical axis the number of parameters in a model, again on a log scale, versus when the model was introduced. And you can see that the number of parameters is increased by factors of 10s to 100s every 18 months. And the current record has reached more than 1 trillion parameters. So, one major problem is that the GPU memory capacity only grows about 1.7x every 18 months, leading to a huge gap between the computation needs of ML models and the capabilities of hardware. This gap is expected to widen in the next few years. So how can we train and deploy super large AI models with limited hardware? And currently, the only feasible solution is parallel and distributed learning, which means using lots of machines to finish the model training or inference together. Beyond the sheer increase in model size, we also face other challenges such as the explosive growth of data. In addition, the underlying architecture and framework diversification is also a big programming problem. We have processors including CPUs, GPUs, TPUs, and so on. And there are different frameworks such as TensorFlow and PyTorch. We need to make it easier to efficiently utilize different underlying hardware and be compatible with different top-level specialization. All these challenges mean that we need the next generation unified deep learning system for the big model era, Colossal AI. It is designed and optimized for all of the above problems and delivers impressive performance. So, but before we delve into our own Colossal AI system, we can look at the existing solutions in the market first. So the existing solutions mainly focus on 3 types of parallel training techniques, namely data parallelism, tensor parallelism, and pipeline parallelism, which we refer to altogether as hybrid parallelism. Horovod is a data parallel training library developed by Uber, and it supports multiple deep learning frameworks such as PyTorch, TensorFlow, and MXNet. Megatron LM is a large model training system developed by NVIDIA. This system supports a combination of all three types of parallel methods. However, it requires expertise in distributed systems, and thus is not friendly to the general user. Microsoft has developed the DeepSpeed system, which enhances data parallel training with its novel zero redundancy optimizer and offloading. It can be combined with Megatron LM to access the tensor and pipeline parallel methods. Google has developed its own ecosystem of distributed training system tools as well. However, most of them are not open source to the community. Meanwhile, Facebook has developed FairScale based on its PyTorch framework. FairScale supports both data and tensor parallelism. Compared to existing solutions, Colossal-AI stands out with more distributed training techniques to maximize the runtime performance. For ease of understanding, we've segmented the architecture of Colossal-AI into 3 layers. Each layer represents an aspect of Colossal-AI that integrates novel state-of-the-art techniques to accelerate training, taking advantage of different hardware systems. It features an efficient memory management system, an automatic n-dimensional parallelism system, and a large-scale optimization-based dynamic scheduler. With these techniques, Colossal-AI can optimize the training efficiency and hardware costs at the same time. In this section, we'll discuss the various techniques used in our system in detail. So in a large-scale training system, the most important feature is parallelizing computation over many devices so as to speed up the job. There are 3 main techniques: data parallelism, pipeline parallelism, and tensor parallelism. Data parallelism involves distributing the training or input data across different processors. Pipeline parallelism separates the different layers in a machine learning model, which allows them to be executed in parallel. And tensor parallelism is a type of model parallelism in which specific model weights, gradients, and optimizer states are split across devices. The 2 best-known systems in the open source community are NVIDIA's Megatron LM and Microsoft's DeepSpeed. Megatron LM uses one-dimensional tensor splitting, as shown in the figure on the slide. The weights of the linear operators are split like this. As a result, large matrix multiplication is decomposed into smaller ones that are executed in different devices. This can allow the model style to scale over a cluster and improve computational efficiency. Microsoft's DeepSpeed is compatible with NVIDIA's Megatron LM and improves the data parallel training through the zero redundancy optimizer, which eliminates memory redundancy. So, in contrast, Colossal-AI includes all the parallel techniques used in NVIDIA's Megatron LM and Microsoft's DeepSpeed. Additionally, it provides the multidimensional tensor parallelism, sequence parallelism, which maximizes the total degree of parallelism. First, let's take a look at how Colossal-AI handles tensor parallelism with its multidimensional techniques. The 2D tensor parallelism is built on the SUMMA, S-U-M-M-A, matrix multiplication algorithm. Compared to Megatron's LM's 1D tensor parallelism, 2D tensor parallelism splits the tensor in a 2-dimensional manner, as you can see here. While the 1D method only splits the weights, 2D methods can split all the inputs, the weights, and the outputs, further reducing the memory footprint in distributed training. While 2D tensor parallelism requires the number of devices to be a square number, such as 4, the 2.5D tensor parallelism is introduced, as you can see over here, to add more flexibility, as the required number of devices can be a multiple of a square number, such as 8. And it also can significantly reduce the communication cost. So in 3D tensor parallelism, we further increase the degree of parallelism such that a tensor is sharded in 3 dimensions, as you can see here. In this manner, we can greatly reduce the communication cost between devices. For example, in 1D tensor parallelism, if we use 1,000 processors in parallel, each processor needs to communicate with the other 999 processors, while in Colossal-AI's 3D tensor parallelism, each processor only needs to communicate with the other 9 processors. So the table on this slide shows the memory and communication superiority of the more advanced tensor parallelism methods compared to 1D tensor parallelism. So if we look, for example, at the bandwidth costs, the 1D case costs a constant amount, depending on the size of the problem. If we do 2D tensor parallelism, it decreases by a factor of the square root of the number of processors. If we use 2.5D, it goes down by another factor, depending on how much memory you have. And if we use 3D, it goes down by a factor of p to the 2/3. All of this leads to significant speedups. So let's talk about another kind of parallelism, which is sequence parallelism in colossal AI. When we're training a model, the memory is consumed by the model, the optimizer states, and the gradients, and input data and intermediate activations. The maximum size of the model in optimizer states is often fixed when we have chosen a specific model. However, the size of the input data and the activations can still vary with data dimensions, such as batch size and sequence length. And so they may become the memory bottleneck when the data dimensions are large. Therefore, sequence parallelism is proposed to reduce the memory footprint brought by large data. So why sequence parallelism? Here, we use the transformer model as an example. In transformer-based models, the space complexity grows quadratically with the sequence length. Thus, when we train models with a 1K, 2K, or even 8K sequence length, the input data and intermediate activations will become the memory bottleneck. Therefore, sequence parallelism splits the full sequence of data into subsequences, and each device only holds a single subsequence, drastically reducing the memory burden on a single device. As a result, the model can be trained on a longer sequence which a single GPU cannot accommodate. This is extremely useful for applications such as document-level text understanding and AlphaFold. So next, we'll do a brief demo about how the computation can be conducted with subsequences on each device. Here is an example of calculating the self-attention score with 4 devices, 4 GPUs. Each device only holds a quarter of the sequence. We can use the ring self-attention module to replace the original self-attention module to obtain the expected outcome. And everything is parameterized by the batch size B, the sequence length S, and the size of the hidden states H. So as each device only holds a subsequence, their query, key, and embedding values, shown as Q, K, and V here, are partial as well. In other words, each device only holds a quarter of all these embeddings. To compute the attention score, we need to multiply the query embedding with a key embedding, as shown here. To begin with, we multiply the local query and key to obtain the partial attention score on the local device. Next, each device will send the local key embedding to its adjacent neighbor, and then calculate the next portion of the attention score. This, to compute the attention score, we need to multiply the, excuse me. This process will repeat for 3 times until each device gets the complete attention score. In this way, each device only holds partial data, but can still finish the computation of the self-attention score by multiplying every query and key. The final attention output is computed by multiplying the attention score with the value embedding, and it can be conducted in a similar manner. Compared with 1D tensor parallelism in NVIDIA's Megatron LM, which is shown up here, sequence parallelism gives us better performance in multiple ways. When increasing the batch size, say from 64 to 128 to 256, the memory consumed by Megatron LM goes up quickly and gets an out-of-error memory, was reported, as you can see here. While the memory consumed by sequence parallelism was almost unchanged, as shown here. When we increase the sequence length from 256 to 512 and so forth, the memory consumed by sequence parallelism is much lower than that of Megatron LM, which is shown over here. So as shown in the figures, sequence parallelism can achieve more than 6 times larger batch size and achieve 1.5 times more speed up compared to Megatron LM when training the BERT-based model. So the horizontal axis shows you the number of GPUs, and the vertical axis shows you either the throughput on this size or the batch size we can attain on this size. Next, we will give an introduction to another important feature of Colossal AI, the efficient heterogeneous memory management module. First, let's get a general idea of data movement on the heterogeneous systems, including GPUs. As a GPU has limited memory to accommodate large-scale models, we can utilize the CPU memory and the non-volatile memory disk to make room for model storage. When training a deep learning model, we can appropriately swap tensors among different devices during runtime. In this case, we only keep the tensors in use in the GPU memory in order to accommodate much larger models. The DeepSpeed system developed by Microsoft has introduced a related technique called zero offloading. Zero offloading resorts to a static strategy to offload the tensors to the CPU memory and the non-volatile memory disks when the tensor has finished computation. However, such a strategy will lead to wasted memory space on both the CPU, as you can see here, and the GPU during different training phases, as shown in the diagram, and therefore this strategy still has some room for improvement. Unlike DeepSpeed, our offloading system is built on the concept of chunk-based memory management. A set of consecutive parameters is stored in a chunk, as you can see here. The memory management system is called Gemini. It utilizes the chunk mechanism to collectively manage the tensor movement. As tensors are grouped into chunks, the bandwidth utilization is higher during data movement. During the first few steps of training, Gemini traces the memory usage at different points of the training step and dynamically generates a strategy to decide whether a tensor should be offloaded to CPU memory and fetched back to the GPU memory. When the GPU memory is not enough, it can evict more of the chunks to avoid running out of memory. So you can see how much the memory here has been decreased because of this strategy. So on the other hand, when there is not enough CPU memory, it can evict fewer chunks to the CPU, which means more chunks stay on the GPU. This can not only avoid running out of memory, but can speed up training. In the later stages, Gemini will also use the collected memory usage information and generate a data movement strategy to finally control the placement of the tensor throughout the training step. In this way, we're able to fully utilize the CPU and the GPU memory for large model training. By using the heterogeneous memory management model, we can tackle the memory bottlenecks in DeepSpeed and achieve higher training acceleration and larger model capacity with limited hardware. With Gemini, we are able to scale up the maximum model size up to 16 times compared to native PyTorch and 2 times compared to DeepSpeed on a typical V100 GPU. So, alongside Colossal AI's fantastic acceleration features, we always uphold the principle of user-friendliness and aim to make our service as easy as possible to use. So, you do not need to be an expert in distributed systems to use Colossal AI. All you need is a few lines of code. Specifically, we provide a unified interface for parallelism strategies in one config file, from which we can configure the parallelism size for data, tensor, and pipeline parallelism, as well as the hyperparameters for the zero sharding and offloading module. We also integrated many helpful features in Colossal AI, such as gradient accumulation and mixed precision training. In addition, we're currently developing an important feature for our Colossal AI. This feature is to provide our system with the capability to automatically parallelize the whole model training process with a combination of data, tensor, and pipeline parallelism. We first trace the whole computation graph in PyTorch to obtain the data flow. Next, we traverse this graph and search for the optimal parallelization strategies for each node in the graph, so that the overall compute efficiency is maximized and communication time is minimized. We annotate the strategy to each node and apply sharding to the node based on the strategy. Finally, we execute the parallelized computation graph on a distributed system for faster and larger scale model training. The whole process is automatic and requires no code change at all. We also enable customization of the search strategies for extensibility. In addition, efficient resource scheduling is very critical for AI jobs. We might encounter such issues in many scenarios like model training or running model inference on the cloud, on supercomputers, or on privately deployed clusters. Another fancy module from the Colossal-AI team is coming soon. Its name is Hiatus, and it's in the beta testing stage. By extending Ray with advanced scheduling algorithms and supporting elastic training, Hiatus can provide high-level resource scheduling for AI jobs. Now, let's take a look at how Colossal-AI is helping us for large AI model training and inference. For a super large AI model, such as GPT-3, Colossal-AI only needs half the computing resources compared to the NVIDIA solution to conduct model training, thanks to its memory-efficient Gemini model. If the same computing resources were used, as shown in this table, the speedup could be further increased by 11%, which could reduce the training cost of GPT-3 by over $1 million. When we apply tensor parallelism from Colossal-AI and set the degree equal 64, we can scale the batch size up to 14 times and reach 5x acceleration in the VIT training. So this plot shows the batch size on this axis as well as the throughput in blue. Similarly, when applying tensor parallelism in comparison to Megatron LM, we see that 11x lower GPU memory consumption and superlinear scaling efficiency in the GP2 training is possible. Using Colossal-AI can actually help us scale up to a 24 times larger model size on the same hardware and reach over 3x acceleration compared with DeepSpeed. In BERT training, Colossal-AI's sequence parallelism helps users reach 2x faster training or make it possible for users to train a 50% longer sequence length. So here the horizontal axes are the amount of parallelism, and the vertical axis is throughput or sequence length. So up is good in all of these plots. When computing resources are very limited, Colossal-AI also delivers eye-catching performance. So for example, Colossal-AI can train a 120x larger model size and higher acceleration even if only one RTX 3080 is available, thanks to its highly memory-efficient Gemini system. For a representative large model, GPT, Colossal-AI is capable of training up to 1.5 billion parameters on a gaming laptop with an RTX 2060 GPU and 6 GB of memory. For a PC with an RTX 3090 GPU and 24 GB of memory, Colossal-AI can train GPT with 18 billion parameters. Colossal-AI can also bring significant improvements to high-performance graphics cards, such as the Tesla V100. On a single GPU, Colossal-AI's automatic offloading strategy provides remarkable performance gains versus the zero offloading strategy by Microsoft DeepSpeed. Users can experience up to a 45% speedup on a variety of model scales. However, when using a traditional deep learning training framework like PyTorch, a single GPU can no longer support the training of models at such a scale. So Colossal-AI is public and available on GitHub. If you feel interested, please go ahead and have a try. For now, we've attracted almost 5,000 stargazers, and the increasing speed is quite amazing, as you can see by this red curve in the figure. And Colossal-AI has been downloaded over 20,000 times up to date so far. We are making efforts on building the ecosystem to help the AI community use large AI models in an efficient and easier manner. Currently, we're happy to contribute to the integration with a number of systems, including Facebook OPT and Hugging Face and PyTorch Lightning. We are quite open to the community and are always willing to provide you any help that you need. So to conclude, thanks for your attention. If you're interested, you can scan the upper QR code to complete a simple survey to let us know how you feel about Colossal AI. This will only take about a minute, and you stand a chance to win a $50 voucher on Amazon. If you'd love to know more about Colossal AI, you can scan the QR code at the bottom of the page to get access to it. So thank you very much for your attention, and see you soon.